What makes Google so good at guessing what you mean when you type a search? In 2018, Google AI created BERT, and in 2019 used BERT to improve Google search, making it better at understanding the context and intent behind user queries. BERT stands for Bidirectional Encoder Representations from Transformers. Bidirectional, it reads text both left to right and right to left. Encoder representations from transformers is related to the paper Attention is All You Need from 2017 that introduces the transformer, a model relying solely on attention without recurrent neural network. Attention mechanism looks at context, meaning the surrounding words. The transformer is composed of an encoder and a decoder. The encoder takes the input sequence, for example a sentence, and generates contextual representations using self-attention and feed-forward layers, capturing relationships between input elements. The decoder produces the output sequence using self-attention, cross-attention, and feed-forward layers. Both rely on multi-head attention and scaled dot product attention, enabling tasks like machine translation. BERT doesn't generate text and it needs to learn the language in order to help with your questions or texts. BERT learns in two main stages. The first is pre-training and the second is fine-tuning. In pre-training phase, it reads massive amounts of text and learns in two ways. One way is masked language modeling. A part of the words in each input sequence is hidden, and the model is trained to predict these original words using the context of the surrounding ones. For example, the Colosseum is impressive. BERT should predict Rome. And the second way is next sentence prediction. BERT sees two sentences and learns if the second naturally follows the first. For example, sentence A, the Colosseum is in Rome. Sentence B, it attracts millions of tourists. The answer, yes, it follows. The second sentence follows the first one. BERT needs both techniques to understand its proper position within the context. Once pre-trained, BERT can be fine-tuned for specific tasks like question answering, sentiment analysis, or named entity recognition. Before we dive into how BERT practically processes a sentence, I would like to take a moment to thank our sponsor, ProjectPro, for supporting this video. ProjectPro is an amazing platform that offers hands-on courses and labs focused on artificial intelligence, data science, deep learning, machine learning, and even BERT-based projects. Whether you are looking to master AI concepts or build a real-world project like the one we are exploring today, ProjectPro provides expertly designed resources to help you level up your skills. Check links in the description to start your journey in AI and data science. Let's use the following sentence. The Colosseum in Rome is impressive. The input text is split into smaller units called tokens. BERT uses word piece tokenization, which breaks unknown words into subword units. For example, the first token is classification, which is a special token added at the beginning. The word Colosseum is split into subwords col, double hashtag, os, double hashtag, The double hashtag symbol indicates that the token is a continuation of the previous token. The sep token stands for separator and marks the end of the sentence. In input embedding section, each token is turned into a numerical vector that captures the token's meaning. This is the vector that represents the word the in the context of the sentence. The vector for Colosseum encodes the meaning of the word and its relationships with the other words in the sentence. The vector for the word in indicates the location or spatial relationship. The vector for the word Rome represents the city and its geographical meaning and context. The vector for the word is represents the fact that the subject is linked to the complement. The vector for the word impressive represents the meaning of the adjective in the context of the sentence. Positional encoding adds information about the position of each word in the sentence. BERT doesn't use recurrence, so it needs a way to know the word order. For example, in our sentence, the word the is in the first position, the word call is in the second position, and so on. Each token gets a positional vector which is added to the token embedding. Multi-head attention uses self-attention as its core mechanism. Self-attention computes attention scores between all elements in a sequence, allowing each element to focus on others. Multi-head attention extends this by applying self-attention multiple times in parallel on different heads, capturing diverse relationships. The results from each head are concatenated and linearly transformed to produce the final output. How does self-attention work? Self-attention applies the attention mechanism within a single sequence using query, key, and value vectors. The query is a vector representing an element asking how relevant other elements are to it. The key is a vector for each element used to measure compatibility with the query, and the value is a vector containing the actual information of each element, weighted by attention scores. Let's assume we are in an amazing restaurant where a customer shouts, "I want chocolate muffins." So we need flour, sugar, and chocolate. The chef is looking on the shelves and he sees flour, sugar, chocolate, eggs, salt, and raisins. The customer's order is the query, what we need. The chef takes the order, which is the query, and checks the storeroom ingredients, which are the key. Flour, sugar, and chocolate match perfectly, so they get big stars. Raisins and salt, they get tiny stars because they are not relevant for this recipe. Every ingredient gets a score. Chocolate 95 hundredths, flour 90 hundredths, sugar 85 hundredths, eggs 60 hundredths, raisins 10 hundredths, and salt 5 hundredths, which is not so much. But how do we make these scores crystal clear? Here comes normalization and SoftMax. Normalization adjusts scores, for example 95-90, to be comparable like a fair scale, so none are too huge or tiny. The SoftMax converts scores to percentages. Chocolate 40%, flour 30%, sugar 20%, adding the rest in small percentages in order to get 100%, guiding the choice of value. Thanks to SoftMax, the chef grabs ingredients which are the values with high percentages. Tons of chocolate 40%, flour 30%, sugar 20%, a few eggs 8%, no raisins because they got 1%, or salt, which is also 1%. In the add and norm section, the output from the attention mechanism is combined with the original input using a residual shortcut connection, meaning we add the input directly to the output of attention layer. This helps the model retain original information and makes training more stable. After adding, the combined result is passed through layer normalization, a technique that normalizes the values to improve training speed and stability. This keeps the training stable and preserves the original information. The feed-forward network is a small neural network, typically a multi-layer perceptron, that is applied individually and identically to each token in the sequence, regardless of its position. It processes the information captured by the attention mechanism. Its main role is to transform and refine the representation of each token after the attention mechanism has gathered context. While attention helps each word understand its relationships with others, the feed-forward network helps process that information deeper. After the attention layer processes the sentence, the token Rome already knows how it relates to words like Italy or capital. The feed-forward network then takes this enriched representation of Rome and further transforms it, helping the model understand its semantic role. For instance, that it's a place and possibly a capital city in the given context. So, the feed-forward network acts as a transformation layer for each token individually, enhancing its contextual meaning before passing it on to the next layer. Add and norm Neural networks can become unstable if the numbers flowing through them are too big or too small. Normalization keeps things balanced. Repeat nx times. To improve the model's understanding, the previous steps, attention and feed-forward networks, are repeated multiple times in a stack of layers. The most popular versions of BERT are BERT-based with 12 layers and 110 million parameters, and BERT large with 24 layers and 340 million parameters. But there are also smaller variants like DistilBERT and TinyBERT, which are optimized for efficiency on devices with limited resources. Let's take the sentence, "The Colosseum in Rome is impressive." At each layer, the model refines its understanding of the relationship between tokens like Rome, Colosseum, and impressive. For instance, in the first layer, the model starts to understand that Colosseum is related to Rome and impressive. In the second layer, the model refines that understanding and begins to recognize that impressive is describing Colosseum specifically. After several more layers, the model's representation of Colosseum and Rome becomes more precise, and it fully understands the context of impressive. Each iteration builds upon the previous layer, enhancing the model's understanding of both local and global context within the sentence.